students, let us continue our crystal structure, that is we have in cubic systems. In the last video, we have seen about simple cubic system. Okay, what is a simple cubic system? Simply, there will be 8 lattice points on 8 corners. Okay, now we have seen in the last class, for cubic systems, you have to evaluate 5 points. Okay, what are they? First one is coordination number. Okay, what is coordination number? Number is number of nearest equidistant neighbors. Okay, for any lattice point on a simple cubic unit cell, the coordination number we should see not only in a single unit cell but in the entire crystal lattice. Okay, so for you take for example, right, as in the last video, right, for this lattice point is at a nearest distance A. This lattice point is also at a nearest distance A. This lattice point is also at a nearest distance A. Okay, so apparently there are 3 in our unit cell. There will be one more unit cell on to our right. Okay, there will be one lattice point here which is also at distance A only. Similarly, in the unit cell just above our unit cell, one more lattice point will be here. Okay, this lattice point also will be at a distance A. So totally 1, 2, 3, 4, 5 are there, and similarly one more lattice point will be in the front of this unit cell. Okay, so for any given lattice point, there will be 6 nearest equidistant neighbors. Okay, so that is coordination number. For simple cubic is 6, we have seen in the last class. Okay, and at what distance those 6 neighbors are present? And at what distance the 6 neighbors are present? That's known as nearest neighbor distance. All those 6 neighbors are at a distance A. So nearest neighbor distance is A. Okay. Next one, atomic radius. I told you, right, whatever is nearest neighbor distance, half of it will give you atomic radius. Okay, it is like this. Okay, if lattice point is here means I'll take that is the center of the atom. The atom will be like this, and one more atom will be like this. Similarly, a lattice point is here means, okay, one atom will be like this and one atom will be like this. Adjacent atoms will be touching each other. All atoms are of same size. They are all rigid spheres. Okay, so in this configuration, if the nearest neighbor distance between 2 neighbors is A, okay, radius of each atom will be equal to, right, A by 2. Okay, see, throughout the crystal structure, remember, whatever is nearest neighbor distance, half of it will give you atomic radius. Take it for granted. Okay, right? So atomic radius are equal to A by 2. Number of lattice points per unit cell. Okay, what have we seen in the last video? Though, right, 8 points are apparently seen. That is, here there are 4 atoms and 4 more atoms will be at the back. Okay, apparently there are 8 atoms in our unit cell, but look, if you concentrate, these one atom is not fully going into our unit cell. Okay, each atom is being shared by 8 unit cells. Remember, say this atom is a common atom for how many unit cells, right? One unit cell will be here. So it is a common for these 2. Okay, unit cell. Similarly, one more unit cell will be on the top of this. One more unit cell will be on the top of this. Means our atom what I have drawn here is a common atom for 4 unit cells in this plane. Similarly, I can bring 4 more unit cells and put them in front of these 4, isn't it? Okay, such that right now our atom becomes a common atom for how many unit cells? 8 unit cells. Means only 1/8 of, right, volume of the atom is actually coming into our unit cells. So what is happening to remaining 7 by 8? They are shared by 7 other unit cells separately. Okay, like this, from every atom I am getting only 1/8 of the volume into our unit cell. So like that 8 are there. So number of actual lattice points present per unit cell is 8 into 1 by 8 is effectively equal to 1. Effectively equal to 1. Okay, next one, packing fraction. Okay, packing fraction denotes how closely atoms are packed in a given crystal structure. Okay, right, now packing fraction, how do we calculate? The volume actually occupied by the atoms by volume of unit cell. Inside a unit cell, how much volume is actually occupied by atoms, how much volume is left out freely. Okay, right, that ratio is known as packing fraction. Okay, this is n into 4 by 3 pi r cube is volume of each atom, where r is radius of each atom. So 4 by 3 pi r cube will give us volume of one atom. If effectively n number of atoms are present in the unit cell, so total volume of all the atoms actually occupied, right, is n into 4 by 3 pi r cube by a cube, that is volume of the unit cell, right? For simple cubic, r equal to a by 2. Okay, so we will get, if you simplify this, you will get pi by 6 r equal to 0.52 or 52% is the packing fraction of simple cubic cell. Means what? A simple cubic unit cell right, is occupied only 52% only is actually occupied. Remaining 48% is null or void space we call. 0.48 or 48% is null or void space. What does that contain? Vacuum. Between two atoms, what do we have? Vacuum. Okay, right? So null or void space. This is not a very closely packed structure. Only 50 or near, only half of the unit cell is actually getting occupied. Remaining half is empty only. Okay. So what is the example? In the entire periodic table, only polonium crystallizes in simple cubic structure at some temperatures. Okay, polonium is the only example having simple cubic structure because nature does not prefer loose packing. Okay, nature always prefers loose packing. Okay, right. So this is about the simple cubic cell. We have what. So now we'll go for what is known as the next Bravais lattice in cubic system. That is body-centered crystal structure. Okay, body-centered crystal structure or cubic eye also we can write. Okay, BCC or cubic eye. Here, apart from 8 lattice points on the 8 corners, there will be one additional lattice point present at the body center. Okay, there will be one additional lattice point present at the body center. And the very beginning we have seen, this is known as body diagonal. Okay, the length of the body diagonal in a cube is root 3a. You have to remember all these points. Okay, length of the face diagonal will be root 2a. Okay, you have to keep all these right values in mind. So one atom is present at half of the length of the body diagonal, that is root 3a by 2 distance. Along the body diagonal, you will have one more additional lattice point. This is known as body-centered cubic structure. Okay, body-centered cubic structure or cubic eye we call. Okay. Now again we have to evaluate coordination number, nearest neighbor distance, atomic radius like that. Now we will see what is coordination number. What is coordination number for this? Simply you can tell. Okay, for the body-centric lattice point or for any other lattice point in the entire lattice structure, if you see, right? See, for this BCC atom, body-centric atom, all the 8 corners are at the same distance, isn't it? Okay, every corner is a distance of root 3a by 2 only. Okay, this atom, this atom, this atom, this atom, all 8 are at root 3a by 2 distance. Okay, so, right, that is the nearest neighbor. Okay, root 3a by 2 is how much? Root 3 is 1.732 by 2, 0.866. In what you call, in BCC we got nearest neighbor distance as a. Okay, sorry, in SC we got nearest neighbor distance as a. In BCC, nearest neighbor distance is decreasing if you observe. It is root 3a by 2 only. Okay, so, right, what is coordination number? Coordination number for BCC, I'll write it as 8 because there are all 8 corners are at equal distance. Okay. If you develop the complete lattice like by putting one more unit cell here, one more unit cell here, one more unit cell like this becomes the body centric lattice point. Okay, see for this unit cell, this is corner, this is body center. If I draw another unit cell like this, okay, this becomes body center, this becomes corner atom. Okay, it's a 3-dimensional infinite array of lattice points, isn't it? Okay, so any atom, depending on the way you construct the unit cell, will be at the body center or in one of the corners. Okay, so coordination number for BCC equal to 8, you can write. So nearest neighbor distance, at what distance those 8 neighbors are present? Root 3a by 2. Root 3a by 2. Okay, right, now what is atomic radius? Blindly you can tell half of whatever is nearest neighbor distance is atomic radius, or we can we can elaborate it. Okay, I can illustrate it better like this. Okay, right, now this is our body diagonal. Okay, at the body center one atom is present like this. Adjacent atoms should touch each other. I told you all atoms should be of same size. Okay, so total length of the body diagonal is root 3a. Okay, how many radii are there? 1, 2, 3, 4 radii are there. From here to here, R. So root 3a equal to 4r, or r equal to root 3a by 2. Or half of the nearest neighbor distance also can be taken as atomic radius. Okay, so if nearest neighbor distance is root 3a by 2, right, atomic radius will be root 3a by 4. Root 3a by 4. Okay. Now again, number of lattice points per unit cell. Now you don't have to break your brains, right? You simply can understand where are we having atoms? Atoms are on the 8 corners. Are all corner atoms belonging to our unit cell only? No, we have seen only effectively one unit cell. One atom only is coming into our unit cell. From 8 corner atoms, effectively only one atom is coming into our unit cell. What about this body centric lattice point? this body-centric lattice point is not being shared by any other unit cell, isn't it? Okay, because one more unit cell on the right will have its own body-centric lattice point. Okay, so this body-centric lattice point is exclusively belonging to our unit cell only. From 8 corners, I am getting one effectively and one body-centric one. So effectively, right, I'll write the number of lattice points per unit cell in BCC as 8 into 1 by 8. Okay, this should remind you that we are talking about corner atoms. Then plus 1. Plus 1. Okay, that is nothing but body-centric point which is not shared by any other unit cell. So effectively, the number of lattice points per unit cell in BCC equal to 2. Okay, now you go for packing fraction. Okay, what is packing fraction? N into 4 by 3 pi r cube by a cube. Okay, that is n equal to how much? 2 into 4 by 3 pi. What is r? R radius of each atom in BCC? Root 3a by 4. Okay, root 3a by 4. So root 3a by 4 whole cube by a cube. Okay, a cube and a cube gets cancelled. If you simplify this, right, you'll get, right, what do you get? 0.68. 0.68. Okay, in terms of fraction also you should remember I told you, right? So that is nothing but our 8 by 3 into 3 root 3 by 4 cube. 4 into 4 into 4. Okay, pi is also there. Okay, 3 gets cancelled. Okay, 4 2s are 2. That is root 3 pi by 8 you will get. Yeah, root 3 pi by 8. Okay, root 3 pi by 8 you will get. Remember this also in the exam, directly this question also comes. Okay, right? And how much is root 3 pi by 8? Take pi as 3.14, you get 0.68 or 68%. This is somewhat better than the 0.52 of simple cubic, isn't it? Nearly 70% of the unit cell is actually getting occupied by atoms. Okay, slightly better than, much better, not slightly, much better than our simple cubic unit cell. Okay, right? So this is what you call BCC. Okay, packing fraction is, remember, root 3 pi by 8 also remember it. This also comes in the exam directly. Or if you simplify that further, you'll get 0.68 or 62%. So 68%. So what is null or void space? Null or void space is 1 minus 0.68, that is 0.32. Okay, 0.32. Okay, 32% of the unit cell in BCC structure is actually void space or null space. It contains nothing, simply vacuum. Okay, right? So now what are the examples of what you call elements having BCC structure? Okay, all alkali metals. Okay, all alkali metals like lithium, sodium, potassium, all first group elements. Okay, first group elements. What first group elements are called? Alkali metals. Alkali metals. Okay, all alkali metals like lithium, sodium, potassium, cesium, rubidium, etc. have BCC structure. Next one is alpha iron has BCC structure. Iron has, at up to one temperature, iron will have BCC structure. Beyond a particular temperature, it will go into FCC. Okay, that is known as beta iron, gamma iron, like that. Okay, so what is alpha iron? Alpha iron is iron what we see in our everyday life at normal room temperatures. Okay, so alpha iron. Okay, and chromium is also another example of BCC structure. Okay, so these are all the elements having, right, BCC structure. Okay, now next we will go into what is known as FCC structure, face-centered cubic structure, or, right, FCC. Cubic F we can write. Okay, face-centered cubic structure, FCC, or cubic F. Okay, here also again draw one cube. Okay, by the time you complete this cubic structure, you will draw in cubic cubes nearly 100 times. Okay, right? You don't need a scale to draw any cube further. Okay, right now in BCC, why in FCC, what happens is there will be 8 lattice points on the 8 corners. There will be 8 lattice points on the 8 corners. Okay, apart from that, a cube has 6 faces. At the center of each face, there will be one additional lattice point. Okay, like this. Okay, center of top face, one additional lattice point will be there. Center of left face, one additional lattice point will be there. Center of bottom face, one additional lattice point will be there. Center of front face, one additional lattice point will be there. Center of back face, one additional lattice point will be there. and center of right face, one additional lattice point will be like this. There is no body centric lattice point, remember. Okay, that's also previous IES question. Okay, right? In FCC, there won't be any body centric lattice point, right? Only the atoms will be found only on the 8 corners and the centers of each face. How many faces will be there? 6 faces are there. So 6 face centric atoms will be now. Now look at this face centric atom. Okay, what is total length of the body diagonal? Total length of the face diagonal. Okay, we have seen that it is equal to root 2a. Length, because this is a and this is a, length of the face diagonal is root 2a. Now, what is the distance between this atom and this atom? Right, that is half of the face diagonal. That is root 2a by 2 equal to a by root 2. What is a by root 2? 0.707a. Means the distance between two nearest neighbors is coming down. In simple cubic, it is a. In BCC, it is 0.866a. Now it is just 0.707a. 1 by root is 0.707. Okay. So this is the nearest neighbor distance. This is the nearest neighbor distance. Okay. If atoms are here, right, lattice point is present here means atom will be like this. Atom is present here, lattice point means atom is like this, right? One atom is like this. And because these are the closest atoms, okay, these two atoms are at a distance. Whereas these two atoms are at a by root 2 distance, that is 0.707a. Okay, so the adjacent atoms touch each other, we have seen. So this is one radius, this is second radius, this is third radius, this is fourth radius. Okay. 4 are equal to, right, root 2a, or whatever is nearest neighbor distance, half of it will become the radius of each atom. So what is r equal to? R equal to a by 2 root 2, we can write. R equal to a by 2 root 2. Okay. Now, what about packing fraction? Okay, so sorry, we can calculate packing fraction from this. Okay, what about coordination number? Okay, this is very, very crucial here. Okay. Right, coordination number means you take any lattice point. For clarity, for easy understanding, I am taking the face centric lattice point. Okay, what is true for face centric is true for corner lattice point also. Okay, now for this face centric lattice point, these 4 atoms on the 4 corners are at a distance of a by root 2. Okay, are at a distance of a by root 2. Right, now, if I want to go to this corner from this atom, how do I go? I'll go a by 2 distance up like this and a by 2 distance towards my right. Okay, similarly, to reach this lattice point, I'll go a by 2 distance like this and to left a by 2 distance. So what is the distance between these two lattice points? Root of a by 2 whole square, a by 2 whole square, that is a by root 2. For the same is the case in this also. Now, what about this lattice point? If I want to reach this lattice point, I have to go up by a by 2 distance, travel towards my right into the unit cell a by 2. So this face centric lattice point is also at a distance of a by root 2 only. Similarly, back face centric lattice point. How do I go to back face center? I will go right along this, right, parallel to the what you call z axis by a by 2 distance. And to reach the back face center, I'll go a by 2 distance, such that this distance also will be a by 2 whole square plus a by 2 whole square under root a by root 2 only. Similarly, right, bottom face center. How do I reach bottom face center? I have to travel straight a by 2 distance and then a by 2 distance like this. A by 2, a by 2. This also will be at a distance a by root 2. Similarly, front face center also will be at a distance a by root 2. Means, for this lattice point, all 4 corners are at same a by root 2 distance, and these 4 face centric lattice points are also at the a by root 2 distance only. So totally how many? 1, 2, 3, 4. 1, 2, 3, 4. Okay, 8 lattice points still now. Same will be the case with lattice points lying in the another adjacent unit cell also. Okay, here also one face centric lattice point will be there. How do I reach this face centric lattice point from this one? I'll go a by 2 distance up. If I go right, I'll get this atom. If I go left, I'll get this atom. If I go towards this way, I'll get this atom. If I go this side, I'll get this atom. A by 2 distance. Means even this lattice point is also at a by root 2 distance only. Okay, similarly, the one on the face, back face center, the one on the front face center, the one on the bottom face center. See, how do I reach the bottom face center of from here to here? I have to travel a by 2 distance. If I go a by 2 distance, I'll reach this lattice point. If I go a by 2 distance like this, I'll reach this lattice point. If I go a by 2 this way, I'm reaching this face centric lattice point. All I have to do is what? Go a by 2 distance like this. Means right? Totally how many? 1, 2, 3, 4. 4 lattice points on this unit cell, 4 lattice points, right, on the 4 corners, and 4 face-centric lattice points in the this unit cell. Totally, right, 12. Coordination number is 12. Remember, for a sphere, for a circle, I'll give you one coin, okay, some 10 rupee coin or 5 rupee coin, right? How many coins you can arrange closest such that all coins touch each other? Okay, this is a common sense question, okay, which comes in that mental reasoning, etc. Okay, right? For one circle, how many circles can be arranged touching it? Okay, like this: 1, 2, 3, 4, 5, 6. Okay, for one circle, we can make 6 circles touch each other. Similarly, for one sphere, one cricket ball, how many cricket balls can be made to touch? Okay, remember, see, for one cricket ball, you can make 6 cricket balls touch each other. But 3 dimensional space, no. You can put 3 cricket balls like this on the top. Similarly, 3 cricket balls at the back also. Totally 3 plus 6 plus 3. How many? 12. So one sphere can be touched by how many other spheres of same size? 12. Remember, that is the maximum. Okay, possibility according to geometry. Similarly, maximum coordination number in solid state physics also is 12 only. Remember, okay, because atoms are spheres. How many atoms can touch one an atom of same size? Okay, 12 atoms only can touch. Okay, that is coordination number 12 is maximum. Remember, in entire solid state physics, what is the maximum possible coordination number? 12. Okay, so coordination number is 12. Okay, coordination number is 12, right? Coordination number is equal to 12. Okay, nearest neighbor distance. Nearest neighbor distance is equal to, we have seen, A by root 2. Okay, atomic radius are equal to atomic radius. Okay, atomic radius are equal to half of this, A by 2 root 2. Now, number of lattice points per unit cell. Number of lattice points per unit cell equal to. Okay, similarly, we have seen 8 corner atoms are there. Okay, 8 into 1 by 8. Effectively, 1 will come. So I'll write it first here. 8 into 1 by 8. Plus, additionally, 6 face-centric lattice points are present, isn't it? Additionally, 6 face-centric lattice points are present here. At the center of each face, right, one additional lattice point is present. At the center of each face, one additional lattice point is present. Now, this face-centric lattice point is shared by how many unit cells? Just like a window on a wall is a common window for 2 rooms only, that's all. Okay, one corner is a common corner for 8 rooms. Okay, but a window on the wall or a door can be a common door for 2 rooms only. Okay, if I have one window in this room here, that window becomes common for me and the fellow on the other side of that room also. Okay, this room also, isn't it? So what is my share of the window? My share of the window is half only. So each face-centric, this face-centric lattice point is shared by our unit cell and the unit cell on the top of this. So what is the fraction that is actually coming into my unit cell? What is my share in this atom? Only half. Okay, half, effectively only half atom is coming into my unit cell. Like that, 6 face-centric lattice points are there. So effectively, right, half into 6. So totally, what is the number of lattice points per unit cell in FCC? Okay, right, 8 into 1 by 8 from corner atoms, 6 into face-centric points. 6 are there. From each one I am getting only half. That is equal to 1 plus 3 equal to 4. Okay, so right, the number of lattice points per unit cell in FCC is 4. Okay, 1 from corner atoms and 3 from face-centric atoms. Okay, usually from corner atoms, write like this: C by 8 plus I by 1. Okay, or I by 1 plus F by 2. You take like this. Remember this. Okay, from corner atoms, effectively only 1 by 8 will come. From body center I, effectively 1 atom will come. Okay, from face-centric atom, effectively only half atom will come. Okay, remember this formula. Okay, for easy remembering easy. Okay, Otherwise, if you know the concept, you don't need all the shortcut formulas. Okay, right? So now what is packing fraction now? Now what is packing fraction? Say, what is that? N into F equal to N into 4 by 3 pi r cube by A cube. The same formula. Okay, right? Now effectively how many atoms are present? 4 atoms are there into 4 by 3 pi. Okay, what is r radius of each atom? A by 2 root 2, A by 2 root 2 whole cube by A cube. Okay, if you simplify this, okay, A cube and A cube gets cancelled, 4 by 3 pi A by 2 root 2 whole cube. 2 root 2 whole cube is 2 cube into root 2 cube. That is around, okay, whatever it is, simplify. Okay, right, take this as a small exercise from your side, right? I'm giving you directly the expression, directly the fraction. Okay, it is 0.74 or 74%, remember. Okay, simplify and you'll get some expression just like pi by 8 root 2 like that. Okay, you have to remember that, right? That also comes in the exam, I'm leaving it to you. Okay, right? So 0.74 or 74%. Therefore, null or void space equal to how much? Null or void space is equal to 26% only. That's all. Okay, means FCC is the closest to packed structure. 76% of the unit cell is actually occupied by atoms. Okay, only 26%, 74% is actually occupied by atoms. Only 26% is left out. That's all. Okay, that's why FCC is known as close packed structure. FCC is known as close packed structure. Okay, so I told you nature prefers close packing. Okay, simple cubic is a very loosely packed structure, right? That's why only one element in the entire periodic table crystallizes in simple cubic form. BCC is somewhat better with 68% occupancy. Okay, about 13 elements in the periodic table crystallize in BCC structure. Okay, here, right, about 16 elements in the periodic table crystallize in FCC structure. Okay, right, because it's a very closely packed structure. Okay, closest packed also. Some books call it as close packed, some books call it as closest packed structure. Okay, right, whatever it is, 74% is the maximum possible packing fraction in solid state physics, remember, and 12 is the maximum coordination number. Okay, right, now what are the examples? All the three, right, elements, the noble metals, all the three noble metals like copper, silver, gold. Okay, copper, silver, gold, they crystallize in FCC structure. Aluminium crystallizes in FCC structure. For electrical engineering students, silver is the best electrical conductor, the best thermal conductor, first best thermal conductor. Okay, and first best electrical conductor also. Next comes is copper. Okay, conductivity of copper is only 15% less than that of silver, that's all. Okay, next best is gold. Okay, next best is aluminum. All four. And in electrical industry, which elements are used widely? Copper and what you call aluminum are used for wiring, and silver is most widely used in contacts. Silver contacts are very, very important in electrical industry. Silver rate is going up or coming down, not because of marriage season also. People think that marriage season is coming, so silver rate is going up. Silver rates will not go because of marriage season. If the electrical industry is booming, okay, they need a lot of silver. Silver is going up means electrical industry is in the boom, remember. Okay, silver is most widely used in electrical industry. Silver metal is most widely used. Okay, of course, to some extent, gold also is very rarely used as a contact material. Okay, we'll see in our laptops, in systems, when we put 4 GB RAM or 8 GB RAM, you will find that gold coating will be there. Okay, of course, gold is very expensive, silver, so they are used, right, sparingly and wherever required for their specific advantages, people use. But in wiring, mostly it is aluminum. Okay, large industrial bus bars carrying hundreds of amperes of current. People won't prefer copper. People prefer aluminum, though its current carrying capacity is less than that of copper. Okay, aluminum is preferable because mass is less. Okay, weight of aluminum will be less comparatively. Okay, right? Copper, of course. Copper has copper advantages. Okay, right? So copper and aluminum are widely used in the electrical industry in wiring purposes. Okay, right? And for conduction purposes, silver is used as electrical contact material, widely used as electrical contact material. Gold is also sparingly used as a contact material. Okay, right? So All these are having what we call FCC structure only. Nickel also has FCC structure. Lead also has FCC structure. Okay, this nearly 16 elements in the periodic table crystallize in FCC structure. FCC structure. Okay, right. So remember some examples and right. So this is about cubic systems. Okay, cubic systems, there are 3 Bragg lattices. If only 8 atoms are there on the 8 corners, it's known as simple cubic unit cell. Okay, right. If an additional lattice point is present at the body center, we will call it as BCC structure. Okay, right. If there are no body centric lattice point, only face centric atoms are there along with the corner atoms, we'll call it as FCC structure. Okay. So I told you in the beginning why we concentrate more on cubic structure, because see 16 plus 13, 29 elements plus 1, 30. 30 elements out of 92 elements in the periodic table. Remove gases and liquids. Okay, in solids, 30 are in cubic systems only. No, isn't it? 30 are having cubic systems. So we study more about cubic system. Okay, right? So this is about the structure. Remember, okay, when we are going into other topics like why we prefer what we call iron, how to make steel, we use this. I will come back to this point again. Okay, right? What do? Iron has BCC structure. I told 32% vacancy, 32% void space is there. In the 32%, I keep putting carbon atoms, small carbon atoms, such that these carbon atoms go and jam pack that iron structure. Right? Iron atoms cannot move, so it becomes harder. Okay, steel is 6 times harder than iron. Okay, like this. So again, we'll come back. Means these structures are very, very important. You have to remember these coordination numbers. That's why in exams also you get the packing fractions of SC, BCC, FCC, all 3 will come in one only. 0.52, 0.68, 0.74 or pi by 6, that root 3, pi by 8, something like that. And for this also expression, okay, they'll give you directly 3 questions. Or void spaces in 3, SC, BCC, FCC, like that. Questions will come. Okay, all put together will be coming. Or if it's a descriptive exam, right, show that FCC and HCP have maximum packing fraction of 0.74, like that. If that question is coming for 6 marks or 10 marks, okay, means you have to, what I have derived now for FCC, you have to derive and come up to this point. For HCP also, which I am going to discuss now, you have to derive that. You will be given some 6 to 10 marks depending on, okay, the way it comes. Okay, so this is about the cubic system. The next topic is, we will go into what is called HCP structure, hexagonal close packed structure. Hexagonal close packed structure. Okay, hexagonal. Okay, close. Hexagonal close packed structure. Okay, you can write this as HCP in small letters or HCP in capital letters. Doesn't matter, all are equally popular. Okay, hexagonal close packed structure. The name itself is close packed structure. Okay, right? Now we will see, this is another important structure which is useful in our material science. Okay, right? Now, what is this hexagonal close packed structure? Okay. In hexagonal close packed structure, the structure will be like this. Okay. I'll draw first one regular hexagon. All sides are equal, like this. Okay. Now, okay, this is a hexagon here. Okay, side of the hexagon is A, means all sides are A only, like this. Okay, this is known as height of the unit cell. Height of the unit cell, I'll take it as C. Okay, right? This is a hexagonal unit cell. Here, the atoms are present on the 8 corners. Atoms are present on the 8 corners like this. Sorry, 6 corners like this. 1, 2, 3, 4, 5, and 6. Okay. At the face center, one additional atom will be present. At the bottom face center also, one additional atom will be present. Okay. Side of the hexagon is A. Height of the unit cell is C. Okay. In hexagonal structure, right? The ratio CYA, remember this is a previous IES question, electrical engineering. Okay, I think 2014 or 15 one question has come. The CYA ratio in a regular hexagon is a straightforward question has come. Okay, CYA ratio, that is height to side. Okay, A was equal to root 8 by 3. Remember, root 8 by 3 or 1.63. Root 8 by 3 or 1.63. In the question directly, CYA ratio is root 8 by 3. Also may ask 7 by 3 or 6 by 3, something like that, or 1.63, 1.74, like that. Okay. So remember both. CYA ratio is equal, you don't have to derive that. Okay. It is a geometrical derivation. Right? CYA equal to root 8 by 3 equal to 1.63. Now, in a hexagonal unit cell, we have atoms here and 3 additional atoms will be present inside the box like this. Inside the box like this, 3 additional atoms will be present. They are not on the surface of the hexagon, remember, they are inside the hexagon. Whereas these are on the surface. Okay, these are all are on surface. These are inside the box. Inside the box. Okay. Right, and this distance also will be A only. Okay, these 3 atoms are also at A distance only, like this. Okay, now we want to evaluate the parameters like coordination number, right, nearest neighbor distance, etc. Right, coordination number. Before going into coordination number, now let us see. This is a regular hexagon, isn't it? So for the face centric, okay, all sides are A only. So nearest neighbor distance is nothing but A. Nearest neighbor distance is A. Okay. Right. Next one. So when nearest neighbor distance is A, atomic radius will be, right, A by 2. So the next one, atomic radius are equal to A by 2. Okay, right? Next one, coordination number. Coordination number means, now look at this centric face centric point here. For this face centric atom, right, all 6 corners are at same distance A. Similarly, these 3 atoms which are present inside the unit cell are also at A distance only. So these 3 plus these 6 plus, similarly, there will be one more unit cell on the top of this unit cell. There also 3 lattice points will be there at a height, at a distance A only from this point. So that 3 plus this 6 plus this 3 is equal to 12. So coordination number equal to 12, right? I told you, right? We have CC coordination number 12. Coordination number 12 is the maximum possible coordination number in geometry itself. Okay, right? So atomic radius is R equal to what? Now number of lattice points per unit cell. This is interesting. Okay. Now we have to carefully evaluate how many lattice points are there per unit cell. How many lattice points are there per unit cell? It is like this. Okay. First of all, 3 atoms are present inside the box. So they are not shared by any other unit cell. So that 3 I am writing here first. Right? Next one. Look at this face centric point. Okay, every face centric point will be divided into 2. Is shared by 2 unit cells we have seen. Okay, this lattice point is belonging to this unit cell. Similarly, the one that is below this unit cell also. So what fraction is coming into my unit cell? Only half of this is coming. Okay, from anywhere, face centric atom will contribute only half into our unit cell. So half from here, half from here. That is effectively 1 atom. That is, I write like this, 3 plus. Okay, 2 face centric atoms. Each one is contributing half. So, right, number of lattice points per unit cell equal to 3 plus 2 into half plus. Now, look at this corner atom. Look at this corner atom. Okay. So, this corner atoms, how many are there totally? 12 corner atoms are there. Now, each corner atom belongs to how many unit cells, or what part of that atom is coming into our unit cell, we will see now. Okay. So, I can draw one more hexagon like this, isn't it? One more hexagon like this. So, this lattice point is common to this unit cell as well as this unit cell also. Similarly, I can draw one more hexagon like this also. Okay. So our lattice point is common to 1, 2, 3. 3 unit cells. 3 hexagonal unit cells in this plane are sharing that unit cell. Sorry, lattice point. Similarly, one lattice point I can consider on the top of this one. one on the top of this one on the top of this one. Means in the other plane. Means in this plane, 3 unit cells are sharing that lattice point. I can put 3 more hexagonal unit cells on the top of these 3. Okay, such that this lattice point become common to, right? Totally how many? 6 unit cells. Okay. First of all, in this plane only 1, 2, 3 hexagons are sharing that. So, right, 3. Effectively, I can put one more hexagon on the top of this, one more hexagon on the top of this, one more hexagon on the top of this. So, our lattice point will become common to these 6 unit cells. So, what fraction is coming into my unit cell? Only 1/6 is coming into my unit cell. Okay, 1/6 is coming into my unit cell. Like that, every corner atom is what you call contributing only 1/6 into our unit cell. So how many corner atoms are there? 6 from the bottom face, 6 from the upper face, 12. So 1/6 into 12 is equal to how much? Tell me. 3 plus 1, 4. 4 plus 2, 6. That is, right, number of what you call lattice points per unit cell. Number of lattice points per unit cell is equal to 6 in hexagonal cubic system, hexagonal close packed structure. Okay. Now we can go for what is known as packing fraction. Okay, what is packing fraction? F equal to, right, number of atoms effectively present in our unit cell into volume of each atom 4/3 pi r cube by volume of the unit cell. By volume of the unit cell. Normally in the class we ask the students, because we have all the parameters now, we'll ask the students to evaluate packing fraction. Okay, right, when we ask them to evaluate the packing fraction, 90% of the students, right, do like this. So number of lattice points per unit cell is equal to 6 into 4/3 pi. R radius of each atom is how much? A/2 I told. Okay, R equal to A/2 whole cube by A cube. Let's get A cube they do, right? They'll get something like pi. Okay, 90% of students, right? Every year, in every batch, right? Most of the students, right, do like this and they get pi. Packing fraction, can packing fraction be pi? Pi means 3.14. Okay, 3.14. Okay, in the last video we have seen packing fraction cannot be equal to 1 or greater than 1. Okay, right? It should be less than 1 only. But unknowingly, or what you call, unconsciously, they will get, sir, pi answer. Where did they go wrong? Okay, in simple cubic, in BCC, in FCC, right? We have substituting volume of the unit cell as A cube. So with the same habit, they'll put A cube also. Here they'll get pi. Okay, but here the structure is not a cube, so that its volume is not A cube. Okay, we have to substitute the volume of the hexagon. Okay, volume of the hexagon we have to substitute. This is where most of students do go wrong. Okay, in the classroom. Right, now, what is volume of the hexagon? Of course, even I don't remember the volume of the hexagon just like that, but we can easily find out, isn't it? What is a regular hexagon? Regular hexagon is like this. Okay, there is, right, this side A. So this side is also A. Okay, this is nothing but an equilateral triangle. Find out the area of the equilateral triangle, multiply with 6. Okay, you'll get the top face area by what you call the length of the height of the hexagon. Okay, C. Okay, that you can do, isn't it? This area of an equilateral triangle into 6 into multiply by C. So what do you get if you do, right? It is nothing but 3 root 3 A square into C by 2. Okay, this is volume of the hexagon. Remember this, if you remember, well and good. Otherwise also you can just derive in half minute then and there. Okay, 3 root 3 A square C by 2. So if you simplify this, okay, if you simplify this somewhere, you'll come across that ratio C by A. Okay, C by A ratio is equal to root 8 by 3. Root 8 by 3 means what? Okay, root 8 by 3 means 2 root 2 by 3. Okay, A by C you will get somewhere, substitute there 3 by 2 root 2 and simplify. You will get 0.74. Okay, 0.474, same as what you have got for FCC. Okay, so hexagonal close packed structure is also a very closely packed structure with a maximum packing fraction of 0.74. Therefore, null or void space here also will be just 26%. That's all. Will be just 26%. Okay, hexagonal close packed. So here we can give you the conclusion that both FCC Okay, both FCC and HCP have the maximum packing fraction of 0.74. Okay, maximum packing fraction of 7.74 and are called close packed structures. Nature prefers close packing, remember. Okay, nature prefers close packing. They are called close packed structures. Okay, right. So maximum packing fraction in the periodic table, nearly 22 elements in the periodic table crystallize in HCP structure. Okay, examples are magnesium, beryllium, okay, cadmium, okay, beryllium, B, okay, cadmium, right, magnesium, okay, zinc, vanadium, zirconium, like that. We have 22 elements in the periodic table. Okay, zinc, right, Zn, and zirconium, Zr. Okay, right, vanadium. These are all what you call HCP. Okay, so most of the elements in the periodic table in nature crystallize in HCP structure at room temperatures. Okay, right. Now, sir, both are having same packing fraction, right? Why there are more elements in HCP than in FCC? Okay, HCP is more stable at low temperatures. FCC is more stable at higher temperatures. Okay, normal temperatures. Okay, right? HCP structure is more stable. That's why most of the elements in the periodic table crystallize in HCP form. Okay, so 22 in HCP, 16 in FCC, 13 in BCC. Mostly near 60 to 70% of the periodic table is by what you call we are studying, right, are having only cubic and HCP structures. Okay, so this HCP structure means don't get confused, right? Knowingly or unknowingly, everyone, all of you, and including you and including me also, we will be using this HCP structure, knowingly or unknowingly. We don't know that it is HCP. Okay, but we will be using that every day, right? How have you seen a fruit vendor arranging fruits on his push cart? Okay, a push cart is like this. Okay, a fruit vendor has to arrange fruits, right? Watermelons or tarboos or karboos, whatever it is. Okay, right? How will he arrange his fruits on the push cart? Or even if you see a fruit vendor in a fruit shop also, how apples are arranged. Okay, how apples are arranged. Okay, first layer he will be putting like this. First layer he will put like this. Okay, the one lowest layer is over. The next one, if you observe, the next one, second layer, where will you put? Second layer of fruits. He won't put fruit on fruit, fruit on fruit, fruit on fruit. No. Okay, he will put the next layer in the gap between these fruits like this. Okay, right? Again, third layer, again, one gap will come here. He will put like, means that pyramidal structure, that's nothing but HCP only. Because there is no support, it comes like this. Okay, it looks like a pyramidal structure. It is nothing but hexagonal close packed structure. Okay, knowing, because that is the most stable configuration. If you does not put it in that way, he cannot put FCC structure like face on for fruit on fruit, fruit on fruit. It's not stable. It keeps on falling down. Or he cannot simply pour all his what you call tarboos or karboos onto a pushcart and keep on pushing. Okay, even if a small speed breaker comes or a small pothole comes on the road, all fruits will be falling down. But if you arrange fruits in this manner, okay, it can withstand small disturbances. Here, a small what you call speed breaker comes, a small pothole comes on the road, or some cycle fellow comes and hits also. This thing will not get disturbed so easily. Okay, this is how fruits are arranged. Okay, knowingly or unknowingly, you did not study material science, no, isn't it? The fruit vendor will not study material science, but still, naturally, you and I also will arrange the fruits in one way, in this way only, after trying other ways 2-3 times. Okay, right? Similarly, all our soft drink bottles, all our eggs, all our apples which come in what you call the carton sheets also, layer on layer, if you observe, right, HCP structure from the side, people carry eggs in trays, people carry apples in trays. Okay, right? It will be like this. If you observe closely, right, one layer of atoms will be like this. Another layer of atoms will be here. Okay, another layer will be here. Like this. This is nothing but hexagonal structure only. Okay, here of course the carton will support. Okay, the carton will support. You will never find egg below the egg in next layer. Okay, always the structure is like this is the most stable one, and what you call the maximum amount of what you call things can be arranged in smallest volume possible. 74% of the volume can be made to get occupied in this manner. Okay, so HCP is nature's most preferred packing fraction. That's why, and it has maximum packing fraction. FCC and HCP both have maximum packing fractions. That's why they are known as close packed structures. In the exam, in the conventional paper, prove that both FCC and HCP have maximum packing fraction of 0.74. Means you have to draw FCC structure, show all its properties, derive its packing fraction. So HCP also have to draw the unit cell. Okay, derive up to what I have done, what I have did, what I did. Okay, then come say that both are having maximum packing fraction. They are known as close packed structures. Okay, right. So this is about the crystal structures. Okay, thank you. We'll continue in the next video. Okay, thank you.